Okay, both of these series are infinitely long because they go on forever, and they're both geometric because they both have a common ratio. So if we look at this first sequence here, or series, I mean, we are multiplying by 4, right, to get from term to term. And over here, you might think of it as dividing by 2, but we could also describe it as multiplying by 1/2, or 0.5, however you want to put it. Okay, so they're both geometric. Okay, so I'm going to look at the sums of these series. So if you're asked for the sum of the first term, well, that's just 3. So the sum of the first term is 3. And then if you ask for the sum of the first two, that would be 3 plus 12 is 15, and so forth. And we get 63 and 225 as we keep adding more and more terms. Okay? And we've got the same kind of thing over here, except I've got a typo there. This should be 10. Not 3 for that first term, because the first term's 10. So then 10 plus 5 is 15, and so forth. Okay. All right. So what I want to look at is the differences between the sums as we're going down this. Okay. So if you look at the difference between 3 and 15, my first two sums in this series, that's a difference of 12. Right? You'd have to add 12 to get from 3 to 15, and then if we look from 15 to 63, that would be a difference of 48. Okay, and then we'd have a bigger jump here going from 63 to 255. That's a difference of 192. So these jumps are getting bigger and bigger from term to term. Okay, let's look at this one over here though. So my first jump is from 10 to 15. That's a difference of 5. And then I've got just a difference of 2.5, and then 1.25. So in this second series, my jumps are getting smaller and smaller. Okay. So this one, as I'm looking at this, these jumps speed up, and this one, the jumps are slowing down. Okay. And that's illustrating a difference between these, okay? So if I added the next term in, this would just keep getting bigger and bigger. So if I think about all the terms in the sequence, which there's an infinite amount of them, you can't really add them up because we're adding more and more to the pot. We're adding bigger and bigger pieces to the pot, actually. So we'll never get there. So this is an infinitely large sum. So you could describe this as infinity, or you might say it has no sum because it doesn't really, you can't really add it up. It just keeps getting bigger and bigger, okay? As opposed to this one, since we're adding smaller and smaller pieces, there's actually going to be a maximum amount, okay? This does have, so for right now, I'm just going to say this exists because we're adding smaller and smaller pieces. We're adding half of what we added in the previous one. So pretty soon we're going to be adding really minuscule pieces to the pot. Okay, and it's true. The sum will keep growing, but it's going to be approaching a certain number that it won't pass. So it has a limit. Okay, so when you've got a sum that's speeding up, or has no sum, we say that this diverges. The sum diverges because as you keep adding it, the totals are getting bigger and bigger and farther away from the last total. Okay, where these numbers are getting closer and closer together because I'm adding smaller and smaller pieces. That means when an infinite sum does exist, it converges. Okay. And there's a nice way that you can tell which of the two without actually kind of thinking through the series and adding the pieces up. For a series that diverges, the ratio is going to be more than 1. Or I really should say more than or equal to 1. Okay. You can have, it's technically, this is really, I mean that, so here I've got a ratio of 4, so that is going to diverge, okay? If I had a ratio of -4, it would actually diverge as well. So when I say it's greater than or equal to 1, or it could also be less than or equal to -1. So it's actually technically greater or equal to to the absolute value of 1. So it could be 2 or 3 or 4, but it also could be -2 or -3 or -4. Okay? We just don't want a ratio that's between 1 and -1, because if we got that, then we've got a converging series. So this is when our ratio is going to be somewhere in this zone. Okay? If it's exactly 1, then it's going to diverge. Okay? So there is a formula, but only for infinite sums that exist. Okay? So here's the geometric infinite sum formula. And I'm putting it over here in this column because you can't use it for diverging series. I mean, you can use it, but you'll get an incorrect answer. Okay, so here is the formula. So the infinite sum is going to be equal to the first term, the value of the first term, over 1 minus the ratio. Okay, so let's use that on this particular series over here. Okay, so for this example, my first term was 10, right? My first term is 10, and 1 minus the ratio. The ratio is 1/2 or 0.5. I'm just going to put it in as 0.5 so I don't get a complex fraction there. Okay, so then when I do the subtraction on bottom, 1 minus 0.5 is 0.5. So I've got 10 divided by 0.5. Well, you can put this into a calculator, but if you're dividing by 1/2, that's the same as multiplying by 2, and that means we're going to get an infinite sum of 20. Okay, and it kind of makes sense if you look at this at these sums as we go along. So we'd be adding a smaller piece. We'd get pretty close to 20 pretty quickly, but you'll never quite get there. Pretty soon, if you follow this this pattern out, we'll get to 19.99 and then 19.999 and so forth. So it's going to be approaching this. You'll never quite get there, but that's where we're heading, and it's not going to pass 20. So that is the infinite sum. Okay. So I also want to point out that you can use the formula and get an answer. It's just going to be incorrect. So this is wrong over here. You could say, oh, okay, I'll use the formula. The first term is 3, and I've got 1 minus the ratio. The ratio is 4. So I've got 3 over -1, and it's -3. Well, that's incorrect. I can see it's not heading towards -3, right? You're never going to get -3 when you add those up. Oh, I made a mistake here. 3 over -3. But, whoops, it's not heading towards -1. That's what happens when I talk and do math at the same time sometimes. Okay? But yeah, that's incorrect because you can only use that on a converging series. So it's a pretty easy formula to use, but you also have to make sure you're only using it when the ratio is between -1 and +1. Okay? So looking at this first example here, I'm looking at my ratio and thinking, okay, it's dividing by 2. That's the same as multiplying by 1/2, right? So my ratio is going to be 0.5. So this is going to work. I can use the formula on this. Okay, I got the first term, which is 18 over 1 minus the ratio. Okay, 18 divided by 1/2 is the same as 18 times 2. So this is going to come out to 36. Okay. All right. All right, let's try this next one. I'm going to be dividing by 4, which is the same as multiplying by 1/4, or 0.25. That's my common ratio. Okay, so what am I doing? The infinite sum is going to be the first term, which is 32, over 1 minus the ratio. Okay, so you can put that into a calculator. Just to show you, you could also do this pretty easily by hand. If you think of this as, this would be 3/4, right? So I've got 32 divided by 3/4. Well, when you're dividing by a fraction, that's the same as multiplying by the reciprocal of that fraction. Okay, And then 32 times 4 is 128. Got 128 over 3. And that's going to come out to 42 2/3, or 42.6 repeating. Okay, but that's the same thing you'd get in a calculator if you just did 32 divided by 0.75 as well. Okay, yeah, I got 42 2/3 there, 42.6 repeating. Okay. All right. Next up. All right, I'm looking at this. Okay, my ratio is 5, so this is going to be the first term over 1 minus the ratio. But hang on, no it's not. This is incorrect because this diverges, right? So you'd have to say no solution or no sum or infinity or something like that. So I'm going to say no sum. Okay. Okay, on to the next page. We're going to try a couple of more examples. On the next page, though, we've got sigma notation. Okay, but if you know what you're looking for here, this is actually, if you think about the specific term formula for geometric, my term builder portion is in that format, right? So you can always build out a couple of the terms to find the first term in the ratio, but if you know where to look and you've got k minus 1 or n minus 1 or some variable minus 1 as your exponent, well then this is going to be the first term, and then this is going to be the ratio. So it's kind of nice if you know where to look. It doesn't take much work at all. Okay, so then here is the formula again. Okay, so I've got my first term, which is going to be 4 over 1 minus the ratio, and that's 4 divided by 0.3, and that will come out to 13 1/3, or 13.3 repeating. Okay. All right, so same kind of deal on this next problem. This is my first term, and this is my ratio. Okay, so let's set this up again. Okay, using this formula from right up there, first term on top, that is 5 and as my numerator, and then 1 minus my ratio. Got 1 minus 1/3. Don't just round that to 0.3. It's important that it's exact. Okay. So I'm thinking of that as 3/3 minus 1/3. That means it's 2/3. Okay. And now I'm going to write this, think of it as division. This is 5 divided by 2/3. That's the same as 5 times 3/2. Okay. And that would give me 15 over 2, or 7.5. Okay. All right. Last but not least, first term, ratio. Okay, so you could start setting this up. First term over 1 minus the ratio, but that's going to be incorrect because the ratio is telling me that this diverges. It has to converge like the previous examples in order to find an infinite sum. So this is no sum, or you could say no solution or infinity. Okay, and that's it for the section. See you next time.